Let's have a quick review about induction, and that's the topic D4 for the HL level, the high level in the IB physics. To begin with, we need to understand about the concept of the magnetic flux. So what is magnetic flux? Magnetic flux is defined as the number of magnetic field lines sent through the area. And this is the definition in the mathematical forms. It equals to the dot product of two vectors. The first vector is the magnetic field B, and the second vector is the vector A. So what is A here? You can see here this is a closed surface, okay? And this closed surface will have a surface area as A. Then you have another vector that normal to the surface. So that would be like vector N here, okay? And it's just like a unit vector. So vector A is actually is the it points in the direction that normal to the surface, and it has the length as the magnitude area. Sounds good? Okay, and here we just have these are a uniform magnetic field, okay, B. So magnetic flux here is a dot product. So basically by the definitions of the dot products of vectors, if you want to recall, it's just what? It's just the magnitude of the first vector A, that's just the length of vector A, times with the length of vector B, or just the magnitude of vector B, and times with the cosine of the angle between these two vectors. So if you have a look at this one, this is the vector A, okay, this is the vector B. We can see that this is the angle between them. So that's why you can find this equation. Phi, it is a Greek alphabet called as phi. It's a scalar quantity, right? Because this B here is just the magnitude of magnetic field. A also like the area, a scalar quantity, and cosine also just a value, a numerical value. So phi in the end is just a scalar quantity, it's not vector anymore. And we can see that magnetic flux phi depends on three variables, right? The first thing is the magnetic field strength, the second thing is the area, and the third one is the angle theta. So if you have the B pointing this way, for example, let's say if you got a, let me draw an example here. If you got a circle like this, okay, then we play it like this, and then if you got the magnetic field penetrate through it like this. Oops, my bad. Okay, so you see that for now, we also have the normal vector this way, right? So what is the angle between them? Both of them are pointing in the same direction, right? Yeah, so that's why the theta is equal to 0, and cosine of 0 is 1, right? So that's why this is when we have the flux as the maximum, right? This is when the flux is the maximum, when the magnetic field is perpendicular to the area surface. Okay, so what if we got some cases like this, still the same surface area in that position, okay, but now you got the magnetic field like this. We can see very clearly by the in this case there's no magnetic field sent through the area, right? There's nothing, and now we can see that this is still like the normal vector, right, of the surface. We can see what is the angle now. Yeah, if I move around this vector here, we can see that the angle for now is 90, right? And for 90, the cosine of 90 degree is just 0. That's why the flux here is 0. Understandable, right? Okay, so that's the key. That's the very first key about the magnetic flux. And then we can see that with induction, the phenomenon can be explained and studied through the Faraday's law and the Lenz's law. So this is the heart of the induction. And we can see that when we got the surface area here, the area here kind of like rotating, or if you have like the magnetic field changing its direction, we can see there will be a change in the flux. And if we got a change in the flux over time, you can induce some current that will run around a wire nearby. So we can examine more these examples in the next video. Okay, see you later soon. Thank you.